Hello, and welcome to Materials Unlocked, the podcast where we take a look at the lesser-known subject of material science and try to unlock its mysteries. My name is Dr. Lewis Owen, and I'm a lecturer at the University of Sheffield. In each episode, with the help of some students, friends and colleagues, we're going to delve into a particular topic and hopefully unlock its potential. So on this episode, we're going to think about predicting materials properties. And it's my great pleasure, as always, to be joined by one of our current students. And this week, I'm joined by Josh Berry. Josh, welcome to the podcast.
Hello, lovely to be here.
So Josh, you're in fact one of the students in the research group that I run with Kathy Christophidou, who appeared on an earlier episode. So you're now a fourth year PhD student, is that right?
Yeah, correct.
Yeah.
Final year.
Yeah, a bit terrifying. How are you feeling about it?
Bit anxious. Time seems to be getting faster, but, looking forward to it.
I think that's perfectly natural. So do you want to just tell us a bit about what you're working on at the moment and possibly your background in material science? I seem to think you weren't a materials undergrad, is that right?
No, yeah, I started in physics, also at Sheffield. So I did BSc in physics, then I did a master's in physics, and I was looking at what to do next, and I always enjoyed the sort of materials subjects that you cover in physics. So I liked those sort of solid state physics topics. So the opportunity came to do a PhD in material science, so I just jumped it, and here I am.
So you had some modules at university in your physics degree that were sort of materials related, is that right?
Yeah, they sort of like crossed the barrier between physics and materials, but they never specifically said that we were looking into material science. It was always with a physics sort of lens.
And I assume you did physics then at school at A-level. Did you have materials modules in that? Because I know some of the physics courses have materials modules within them.
Yeah, they contain materials modules, but again, they don't specifically tell you that you're studying materials. They sort of keep it under the umbrella of physics.
Yeah. And now, do you consider yourself yet a material scientist, or do you still see yourself as a physicist? Because I know coming from chemistry, I'm still sort of going, oh, maybe I'm still a chemist sort of at heart. But
no, yeah, I would say I'm in exactly the same boat. I'm still a bit of a die-hard physicist, but with being in the final year of the PhD, it's becoming a lot harder to say that I am a physicist and not a material scientist now.
But do you find it changes the way that you perhaps approach problems compared to like some of your peers or colleagues who might have come from chemistry or engineering or something instead? Do you find that you approach problems in a slightly different way?
Yeah, absolutely. Especially compared to, say, people who have come from material science and are now doing a material science PhD. I find that a lot of the time talking to them, their problem solving and how they reach solutions is often like a complete sort of polar opposite to mine, which sometimes works really well.
I was going to say, very often it's like a complementary skills thing, and you find that together actually it's that breadth of skills that allows you to sort of crack a problem. So what is your research looking at then?
So my sort of area of research is looking at utilising machine learning in material science to try and predict HEA compositions that would be useful for metal tooling applications. So things like drilling and metal forming and things like that, trying to design new alloys that would advances in those fields by machine learning. Yeah,
so high entropy alloys or HEAs are something that we talked about on a previous episode very, very briefly, which are a sort of brand new potential class of materials. And machine learning is one of those things that we go back, I don't know, even 2-3 years, people weren't really talking about it in the way that they are now. And then suddenly, it's sort of everywhere that you go, people are talking about machine learning. And hopefully we can explore that a bit more in today's episode as one of the areas that we're going to cover. But I think that's a good point for me to sort of pivot away from Josh for a moment and introduce my other guests. So today we're joined by two specialists from the department, Dr. Claire Utton, who's a research fellow in the department, and Professor Hector Basoalto, who's a professor of metallurgy. So Claire, Hector, welcome to the podcast.
Hello. Thank you for having us.
Claire, do you want to tell us a bit about your background and the sort of research field that you find yourself in now? Were you a material scientist all the way through, or have you come from somewhere else?
No, I am a material scientist through and through, I think. So yes, I did my undergraduate and PhD in material science, but I've kind of sort of gone across a breadth of materials in my career. So I did my PhD looking at nuclear waste encapsulation.
Right, yeah.
And then sort of moved into nuclear fuels and then learnt this modelling technique that I'll probably talk a little bit about. And then from that, I then started to look at other materials like metallic materials. And so that's the area that I'm currently researching. So I'm interested in materials essentially that can perform in extreme environments, so at high temperatures. So, for example, inside turbine engines, or materials that we can use in fusion or fission reactors.
Yeah, I think that's with material science. There's often this, materials is a very broad field in terms of the actual materials people study. It runs the gamut all the way from the sort of biological materials on one side to, metals and concretes and really solid things on the other side, and everything in between. But very often people may just work on one single material, or as you say, sort of might span over the course of their career, or even at one time several different families of materials, because they're more interested in sort of an underlying principle or an underlying technique or something that sort of runs sort of across between those different things. Yeah. But I think it's fascinating seeing all the different types of materials. And in this series, we're focusing primarily on metals. We're using metals as our example for exploring this materials design cycle and the various stages of that. Hopefully, we'll talk about other materials in the future. So let me turn now to Hector. Hector, do you want to tell us a bit about yourself, your background, your research as well?
I'm a material scientist through and
through.
I just love material science. It's the diversity of the subject and the interdisciplinary nature of it, in the sense that you're dealing with different material systems. But one thing that's really caught my attention since I started doing a material science degree was this idea of what you just mentioned, of concepts that run across different material systems. And not just different material systems, but those concepts can run across processes, obviously to control the structure. I guess we'll talk about that later in terms of properties of materials. One of the most beautiful things about the subject are those themes, those connectivities. Since I got hooked when I was young on this, I went to my PhD. The road for me to try and understand those principles has been through theory and computational mechanics of materials, trying to study the dynamics. And I did my PhD in ceramics. We talk about different material systems.
Yeah.
So I did that, and then when I graduated a postdoc, I was working on metal systems and looking at high temperature behaviour. And then I took a break and I went to industry for a couple of years, which was really great because it opened my eyes in terms of what are the type of problems, the industrial pull that is required for science. What are the questions that we need to be tackling, especially in terms of developing some of those underlying principles. And then I thought, I better go back to university and maybe we can tackle some of these problems. So in terms of my research interest, it's trying to understand theoretically what are those governing principles, in particular over the various structural and length scales and temporal scales that govern materials behavior, and to translate that to computational tools, which people can then use for various purposes. But hopefully that's a kind of a snapshot of what
that's perfect. It's really interesting to hear that you say you spent some time in industry. In the previous episode, we talked about defining the problem and how actually material science sits in order for us to develop a particular material or a particular process to create a material or something, we have to have a really good understanding of the application and that, applied side. And compared to a lot of other sciences and things, I think we work incredibly closely with industry, and you see much more commonly, I think, in material science, again, compared to other sciences, that people have gone back and forth between industry and academia and have the benefits of being able to see both sides and that sort of influence. So it's fascinating to hear that you sort of, it helps you to develop that insight.
Oh, for sure, definitely. Yep.
To find these problems. So I think that gives us a really good place to start from, because talking about industry, in the previous episode where we talked about defining the problem, one of the things that was picked up on was thinking about this idea of modelling in general and how we can use computation in various ways in order to help us design materials, understand materials, and improve materials for the future. And particularly, talking earlier about like machine learning and things, people are becoming increasingly aware, I think, of the power that computation can have to help us in science to accelerate, understand various different processes. So I thought that's probably a nice place for us to start. So Claire, if I turn to you for a second, if we're thinking about designing a new material, I wondered if you could tell us a bit about some of the software that you use and some of the sort of modelling or prediction tools that you use in order to help us predict and suggest new materials and what properties they might have.
So in my research, I use this method called CalFAD. It stands essentially for calculation of phase diagrams. And it's a method that we can use to help us to predict the sort of thermodynamic and kinetic properties of materials. So when we talk about thermodynamics, sort of in comparison, or when we're talking about materials, essentially we're talking about stability of a system. So we can use thermodynamics to tell us how stable a system will be. So for example, if we mix certain elements together, we hold them at a specific temperature, thermodynamics can tell us what will be the stable phases for that given temperature and composition.
So whether or not they'll mix together or form a certain structure or form a different structure or a combination of different structures.
So alloy design, that's quite powerful. So without doing any experiments, we could do lots of calculations, and then we can decide whether or not alloys in a particular compositional range, for example, will give us properties that we're interested in. But this is based on the caveat, though, that we have a database that we trust and is relevant to the system that we're looking at. So that's kind of the most difficult part of this type of modelling is having those databases.
Yeah. So this, just to pick up on this understanding of phases, we're thinking really here of the building blocks, the components that go into our alloys. And so often we'll have an understanding of, a particular type of structure might imbue our materials with certain properties. So by understanding those phase diagrams, as we call them, which show us which structures are going to be, as you say, stable and which are not, we can select particular, regions. But there's a key thing there about translation of sort of our understanding of sort of how we go from these are the phases that are produced to the material's properties. And that's where, there's a real skill that comes in with a material scientist, understanding how particular combinations of phases or particular phases may then affect the properties, where there's a huge amount of study, right, going into these things. You also mentioned this thing about databases and how we require this really good source of data. So when we're typically doing one of these sort of alloy design type projects, we'll use this software in order to predict the phases that we might get. And then where do we go from there? Because at the end of the day, it's a model, right? We don't know how good or otherwise that model is. So I assume we always then have to do some sort of testing in order to validate how good or otherwise that model is.
Yeah, not everyone will do this, but before we use a database, we'll try and validate the database. Yeah, so we do some testing, compare it to things that are already published in the literature. How well does it reproduce that?
Okay.
Yeah. And then we can do these more exploratory type experiments. But obviously, just because you've done a calculation doesn't mean that it's correct. And also these databases as well are all based on the principle of equilibrium. Yeah, so it assumes that everything is in its lowest energy state. But most things in the universe probably aren't at their lowest energy state. So we have things that are metastable, so we have to use a bit of knowledge to understand whether what we're predicting is real or not.
So I think that's one thing that people might not appreciate fully about metallic systems. When we're talking about, what's stable and at equilibrium, sometimes it can take a very long time for these things to form. It's not an instantaneous thing. It can take, tens of hours, hundreds of hours, thousands of hours in order to form these things if, things move very slowly through your material or whatever. So I suppose that's an additional challenge, having this kinetic component that you have to consider as well, and how you combine those two, of the understanding of what ultimately the system is trying to form, but actually what it's formed in a reasonable amount of time, right?
Yeah, that's it. So I guess the famous example is the iron-carbon phase diagram. So if you draw that from a thermodynamic database, it tells you iron and carbon, or graphite will be the stable phases. But if you make that material, you get what we call an intermetallic phase forming called cementite. And if you wanted to form graphite in that system, you'd have to leave it till the end of time. It's like we're talking about those sort of timescales. So
So then by playing with these times, we can, control the material's properties through this process. The other example that I often like to think about, because, of my love of food, is chocolate in this respect, because there's a wonderful diagram for chocolate looking at the stable phases of chocolate that form. And anyone who's had chocolate that's been left for long enough that it's gone off, that's a different structure of chocolate that's formed after a long period of time. And depending on the rate at which you cool, the temperature at which you store it, will affect those phases that you form over that period of time. So Josh, one thing that you've been doing, I know, during your PhD is you've been using this same software in order to predict these things. But with these high entropy materials that you've been looking at, sometimes these databases that we're talking about are a bit more sparse because they're such a new family of material and a new class and a new area of compositional space to explore. People haven't necessarily, investigated that particular material before. So I would imagine that means it's probably quite challenging, some of this phase prediction using these methods.
Yeah, I would say that's very true. One of the main attractions that people put on this high entropy alloy sort of space that we're looking at is just how varied it can be. That's one of the reasons so many people are looking into it, because you can have just so many different types of alloys. But that also then causes problems in terms of the databases, where you can explore areas that are more sparse in the database and not really covered in as such greater detail compared to some systems that have been almost covered to death at this point. You see them coming up all the time. So yeah, you can get a really wide range. And that just means that sometimes when you take the results, you have to be a little bit careful and put a little bit of human intuition into it. Sort of, is this really what I would expect from this system? Can I sort of trust it based on what my intuition is and what my knowledge of how I think the system would behave?
And that's where I think the skill in the material science really comes into play. So then there's quite a sort of circular process here, I suppose, with, you're using these pieces of software in order to predict certain phases, and then you go back and you make a material, see what phases it has within it, understand the structures that are present, what's stable within it. And then I suppose you have to sort of feed back into those databases. So I think, Claire, this is something that you work with some of these people compiling databases. Is that right? To help get that sort of feedback to sort of improve the models that we're using going forward?
Yes, you're right. It is very circular. So the databases essentially are calibrated on experimental data. So they need experimental data. So inside the databases, we have equations that describe the thermodynamics, or something called the Gibbs free energy, of each of the phases and elements that are of interest. And these are essentially optimized to experimental data. And that experimental data can be computational data as well. Okay, so what we call ab initio data. So it's more for what we call first principles calculations to calculate thermodynamic data, but it's also on like phase diagram data. So if Josh was to make material and publish that, and then we could then take that information and then try and incorporate that into a database. But the databases contain mostly sort of more simple information about binary and ternary systems, sometimes four-component systems as well. And then the databases, the way that this CalFAD method works is that they're then extrapolated to higher order systems. So as long as your binary and ternary data is really good and you trust it, you should be able to extrapolate it then to these higher order systems.
It shows that it's quite a powerful piece of software that we're able to do this sort of extrapolation and give us an idea of, exactly what space, what we might expect to get there. And my understanding is that very often it might be that it sort of, gets the broad picture right, but some of the finer detail possibly sort of less accurate. But then hopefully with this iteration process, we're continually improving and making these things better and better so we can, predict our materials better for the next time. Yeah. So the method that you've been talking about is used to predict these phases. I wondered if you could just talk briefly about sort of how people did this sort of thing before we had, these sort of computational tools, because it was really just a trial and error system, right? You took something and, added a bit of something else in and went from there.
Yeah. So it would have been, I mean, I'm sure, but, people would have had experimental phase diagrams, for example, on systems, so they would have had knowledge from that. But yeah, it would have been, I imagine, a trial and error of making an awful lot of samples and then measuring properties of those materials. So it's a kind of a time-saving, money-saving method if you can use this and, as you say, trust the databases, then you can get a lot of information.
Help to select down. And people often talk about, thinking about in a number of fields, but in materials for one, sort of high throughput and the ability to sort of sample a big space in terms of, people talk about this with drug discovery as well. But I suppose that's potentially one of the advantages here is you could sort of investigate a large amount of space and sort of explore that even before. Give us an idea of the sort of timescales that we're talking in terms of how long does it take to do one of these calculations of one of these things compared to melting alloy systems and things. Could you just give us a feeling for those sorts of times?
I say, well, probably Josh has a better idea because he's someone who's done hundreds and thousands of calculations, I think. But it's like per calculation we're talking minutes, but for an experiment, it's days, isn't it?
Yeah.
And weeks. Then you have to actually analyze the data.
Yeah.
And but
Yeah, I was going to say, Josh, do you like to chip in?
I can jump in. So, the actual manufacturing process of making the alloys experimentally, depending on how complex they are, can take a whole day to make them, and then you've obviously got to analyze them. And depending on how complex techniques are, they can take days or even up to a week. But something like this CalFAD method, you can really whiz through a lot of samples in a really short space of time. So I was looking at going through, I think, around 25,000 different compositions. Yeah, it sounds a lot, but in the
sounds a lot.
it's not that many. So I was looking at 25,000, and that took around 2 days to run and give me pretty detailed information on phase formation and some property information as well. So you can get a lot out of it, and it sounds like it takes a long time, but to get through that many different compositions that quickly is a lot faster than experimentally making all of them.
And you mentioned there property prediction as well. So some of these pieces of software are also capable of predicting some materials properties as well as the structures that form. Is that right?
Yeah, so you can get some basic properties out of CalFAD as well as the phase information.
Yeah, that's incredibly useful for helping us, design these new materials and understand what's taking place. So, Hector, the type of modelling that you do is slightly different from this, and looking at a slightly different stage, I suppose, in the materials design process often. So, I wondered if you could tell us about some of the sort of physical models that you tend to use and employ in your work.
Yeah, no problem. Yeah, so that's in terms of the work we're doing, is kind of extending some of the things that you've just heard. So you heard about stability and thermodynamics. A lot of the modeling work that I do is regarding taking the thermodynamics and look at the kinetics, the evolution of material systems. So the type of things that we're interested in terms of understanding will be, we heard the term microstructure, for example. So the microstructure, when you look at any material, from wood, from a piece of metal on your table, whatever it could be, you can zoom in, you can start seeing in small units that make up the materials. Could be small crystallites in metal systems, for example. And those crystallites have structures and they can change. You take it, for example, you put a bit of temperature, a Bunsen burner, and then all of a sudden you see interfaces that are making the structures move. So we're interested as to what are those kinetic principles which are moving those interfaces. It could be precipitation. So, Josh and Claire are talking about precipitation in terms of CalFAD, telling you what phases are there. And we take this kind of extend this to say, okay, how is it distributed? So we have this precipitates, and like you, I like food. So I think of jelly, and you imagine having all these grapes, but of different sizes distributed, and they should start popping in your jelly, right? Because you expose your jelly to temperatures. Now the jelly, it could be a metal system, could be a steel, could be a nickel alloy, for example, and you have this second phase precipitates that are emerging from the matrix because you have this kind of grouping of atoms that form these additional phases that can influence the properties. So in terms of techniques, we're interested in understanding how do we generate microstructures, how do they evolve, because they're important for us to understand manufacturing processes, as well as to understand how structures behave in service in terms of for design considerations. The other aspect that we're really interested in is this interaction with the properties is of defects. One of the most wonderful things about nature is that this artificial concept of perfection is that we're full of defects. It's not true to be, there's no a perfect crystal lattice. And the lattice, crystal lattice, for example, the periodicity breaks down. It could be, for example, an atom could be missing, right? We call that a vacancy. Sometimes we find groups of atoms missing and they form like a spaghetti line in your crystal. We call that a dislocation. And that dislocation, for example, can influence how metals deform. When you take a copper wire and you bend it, you get a lot of these dislocations that generated. So this kind of if it's almost like a pearl of vacancies, threading through, if you like, all together. It's not quite that, but it's just to give you a picture. And the crystal lattice that move around and they deform the crystal. And they give you a deformation we interpret as a property. So we're interested in techniques that talk about defect interaction with the microstructure. We're interested in developing theories that talk about deformation of materials at different length scales. So in this particular case, I was talking about the nanoscale to the microscale. So something of the 1/1000th to 1/1,000,000th of a meter. And then we're also interested in techniques. What happens when you have groups, agglomerations of all these entities, with the mesoscale, so with 1,000th of a meter, how all these various entities behave, and ultimately translate that to a property that we see, like bending a copper wire or a tensile test. Like you mentioned, some of the A-level subjects, you'll learn Young's modulus, and there's a question about the stress versus strain. And, you could ask, how does a stress-strain curve arise? And that for us is as an example of emergent behavior from all these underlying principles. And that's another, so all our kind of computational techniques are based in trying to understand how interfaces move, how defects move, and how they give rise to properties.
Yeah, that's fantastic. So when you're thinking about the things that could affect this and the things that you're modelling, you mentioned temperature is obviously a really important factor. And also I think you sort of implied that also like stresses, forces acting on it. Are they the main two sort of effects that you look at, or are there other effects that you're interested in exploring as well?
Yes, so they're the two main ones.
Yeah.
So to kick off with that, and the main reason for that is that there's in terms of developing ideas. We talked about earlier about this connectivity of principles between material systems. So there's this thing in materials that is actually was developed a while back, but this idea of configurational forces. So what it means is that you talked about your thermodynamics, and what that means in terms of a deforming material is that you have the energy within the material could be varying from one point to the next because it's deformed by different amounts, okay? And because the materials deform at different amounts, the energy required to accommodate that deformation will be different. And it turns out that if you have these changes in this energy, they give rise to forces. Those are what we call configurational forces as opposed to a mechanical force, like pushing,
against a table
or whatever it could be. And the important for us is trying to understand those forces then are driven by temperature fields and could also be driven by mechanical fields that you're imposing on the system. So this connection between this kind of what we call boundary conditions, what we're imposing on the material, i.e. we're putting a metal into a furnace or we are basically subjecting a structure to some load, it gives rise to this kind of energy variations within the material that can translate to forces which can move interfaces, like I mentioned earlier, defects, whatever it could be, and that governs the subsequent properties that you see.
So when you're describing these forces and doing this modelling in order to understand these properties and these interfaces, what sort of scales are we looking at here in terms of the size of the object we can model? Are we imagining that we've got, a small piece of metal that's a millimetre big, or are we thinking about, big steel girders that are meters long, or where on that range are we sitting?
All of the above.
Oh, all of the above, right? So everything.
Everything.
Nice, yeah.
So this is the wonderful thing about in terms of materials. You're dealing, if in terms of the engineering side, you're dealing with structures like an I-beam in a construction site for civil engineering applications, or in aerospace, you have various components of different dimensions from the gas turbine blades, which, a couple of millimeters, you could talk about the disc, which could be much larger, the order of a meter, or type of length scales. So obviously you can do modeling at those length scales. How does a structure behave? How does it vibrate? How does it deform? But then we're interested about the properties, right? And for that, we need to go a bit lower in terms of what we say the length scales. So the next length scale we're talking about maybe is of the order of a millimeter, or maybe a thousandth of a meter. Or it is a millimeter, but I meant to say a thousandth of a millimeter, sorry. So going to a micro scale. And in that regime, you start dealing with some of the things I already mentioned, like in metals will be crystallographic grains, for example. So this group of grains that can interact and accommodate deformation. So we want to understand that. And we basically develop models that try and reconstruct those structures, for example, digitally. And some of the things that we're really interested in is even taking from the experiments images of those structures and digitize those images and trying to reproduce them in a computational environment and study those directly.
I was going to say one thing people often talk about, or I've heard talked about, are digital twins.
That's right.
And this idea that we could create a digital model of a real component or part, and simultaneously, actually deform the object and model the deformation and compare the two and get an idea of what's taking place.
Absolutely. So the idea of the digital twin is you said it quite clearly, is that you have this kind of mathematical representation and a digital representation of some physical object. It could be anything. You could have this physical twin. So it could be an engine, it could be a structure, as you said, you want to see how it behaves, and you're able to reproduce the characteristics of that system within this computational environment. And the important thing about the digital twin is that you've got to have trust that you can actually use a digital twin to help you make decisions. And at the core of that is having predictable models, models that can realistically capture the behavior of your materials and in relation to the functionality of the structure that you're looking at.
Yeah, and I suppose this is where it comes back to a similar thing with the CalFAD of having to, in the CalFAD case, we had this loop going around to feed information back into the database. But in these cases, we've got physical models, but we then need to test that those work and make sure that experimentally they're sound in order to make sure that the digital twins are, or, the modeling
robust
we're doing
enough.
Is really robust.
Yeah.
And this is something we talked about in a previous episode, was this idea that the models that you're talking about are, of course, incredibly useful if we're predicting something before we've made it. But as you say, in this case, we're also thinking about it for an in-service condition where, there might be something, a part that we need to understand how it evolves as a function of time. And very often for us as material scientists, it might be the case that we can't directly get the data we want on that object. Claire mentioned earlier, nuclear waste, where, we can't necessarily wait for thousands of years to see what will happen. So we have to come up with proxy experiments or models in order to try and describe these sorts of things. And I suppose these modeling techniques that you're talking about, Hector, are perfect for this sort of, digital twin with this physical understanding. It means we can predict, if I've got a turbine blade or something in an aircraft engine, what might happen to that over the lifetime of that blade.
No, absolutely. And this has been at the core of trying to develop diagnostic and prognostic methods where you connect now computational models to sensors. Right? And
so getting real-time information.
Information and translating it to get information you don't have access, as you mentioned, readily. So you could imagine even like in the future, non-destructive testing. Right. So maybe in the future, if the computational models are good enough, and obviously we're still working to kind of understand how we develop these models, is that we should be able to maybe do some appropriate signature, ring a component, and from that you'll be able to translate that to some appropriate range of properties or defects, or pick up a defect from that signature. So that I think that's one of the key things about being able to develop physics-based models, which I think is important to be able to do this kind of digital twins. And moving to the future is how do we better start utilizing these models by connecting them to sensors, bringing them to interact with machines, so that you can utilize and exploit those
appropriate
models.
Data to input into
and be able to exploit the models.
Yeah. So with these diagnostic centers, one area that I'm aware with, people are interested in developing sensors to get a lot of this information off, but obviously we've got a huge amount of data coming off one of these machines at any one time. So I would imagine it's just a huge amount of data to process. And I know some people are already talking about how we can use, for example, machine learning algorithms in order to help us sort of direct and guide these or our understanding of that data and identify and then have that sort of real-time feedback. Seeing as machine learning is such a big thing in the news at the moment, I thought we should probably talk about it. So I might turn to Josh here, actually. Josh, do you want to tell us a bit about machine learning and its sort of use and how it's sort of developed in material science over the last few years?
So machine learning really can be applied to almost anything, and people really are trying to apply it to almost anything these days. Anything where there's data available, you can apply machine learning to it, and it can make predictions and give you information about that data. So really, it just goes hand in hand with material science a lot of the time. We have, in some cases, a lot of data available, in some cases, a little bit less data available, but there's always data available to perform these predictions on, and it can really assist us in things like alloy design. So, for example, we talked earlier about the searching the high entropy alloy space using CalFAD, and machine learning can also be used for this purpose because we've got data on the high entropy alloys from the literature, and we can feed this into the machine learning, and then it can give us predictions, tell us what phase it thinks will form for this composition, what properties it thinks it'll have. We can get it to predict almost anything from this data. Is pretty remarkable, to be honest.
Because one of the areas that I think most people are familiar with machine learning, they're aware that it's very good at sort of pattern recognition or sort of identifying. It's been used in image identification, where you train an algorithm to say, is this a cat or not, and that sort of thing. And I suppose we're using it in a sort of similar way, but a slightly different way here, of using it to sort of take things that we know and identify patterns, locations, similarities, to identify certain spaces that might be useful to explore, or in terms of sensors, where we might need to then change something about our process.
Yeah, you talk about pattern recognition. That is very applicable with material science, because we have these alloy systems, and they're going to form certain phases, and they're going to have certain properties, and you can sort of see the patterns across these different compositions forming the phases that they're going to form. So machine learning can really accelerate this sort of discovery of these patterns within material science.
But one of the things that Claire was talking about earlier with the CalFAD system is obviously that we've got a limited amount of data, and we sometimes have to extrapolate out. How does the machine learning algorithms, or how do the machine learning algorithms cope with that extrapolation? Are they quite robust, or can they be quite variable in terms of the quality of that extrapolation?
Machine learning can do the extrapolation, but it's always going to be much better at the interpolation side. So taking the data that you have as the extremes, and then looking at the patterns within the limits of the data you have. So it can do the extrapolation, but there's always a bit of a caveat of you have to be careful of sort of the things that you're predicting, and again using a bit of that human intuition and that sort of human input of, is this really what I would expect? So a lot of the time the things I sort of do are sort of pit the two systems against each other, almost. Machine learning and the sort of CalFAD techniques, and then from the contrast across both of them, you can sort of apply your human intuition and think, is this really what I would expect, and take it from there.
And I suppose as the really successful machine learning algorithms that people often refer to are the ones that have been trained on big data, huge data sets. And I suppose that's one of the things that we need to ensure going forward in material science, is to make sure we're still collecting that data and populating these databases with this information, so we can continue to expand those algorithms and their capabilities.
Yeah, the main drawback with machine learning, especially in the field of material science, is often the lack of high quality and high quantity data. You look at some of the more common machine learning things, something like ChatGPT, which is trained off of millions upon millions upon millions of data points. Typically, you want to be training machine learning off hundreds and hundreds of thousands of data points at least, whereas sometimes in the material science field, we're looking at a couple thousand, couple hundred compositions that people have made, if that, because, as I said earlier, it's time intensive to actually produce these and experimentally verify the information.
And I suppose in some cases it might just be as simple as someone did this study, but it's not in a a referenceable form, right? It's in a hard copy of a paper that someone needs to go and look up and actually type that information into the database in order for it then to appear.
Yeah, absolutely. Even then, when you have digital information available, you end up with not everybody formats it in exactly the same way.
Oh, yes.
So you end up with trawling through a million different ways that people have written the same information.
So just extracting that information, even if it's there, can be a challenge in itself. Oh dear. Well, one question that I had, thinking sort of zooming out for a second. So these modelling techniques are obviously all fantastic in various different ways for, predicting phases or understanding how phases develop, or the physics or the structures develop. I suppose a question, just thinking for a second about computational power that's required, because part of the reason that this is has accelerated so quickly over the last 10, 15, 20 years is because of our advantage in computational ability. But at the same time, there is surely a sort of an energy penalty associated with, maintaining servers to do these sorts of calculations. So I wondered if we go around and if you could all give me an idea of sort of the computation that is required for these different techniques that we've been talking about. I mean, Claire, we sort of talked about this earlier, that it was sort of on the order of, maybe minutes or hours or days, depending on the complexity. But are you doing these things on a laptop? Do you need to go to a supercomputer? What do you need to do these sorts of calculations?
Generally, it's just a normal desktop computer.
I mean, that sounds fantastic. You can...
So if you want to do it quicker, then you maybe want to use something. Well, if you've got lots and lots of calculations, or you want to get them done quicker, then you want to go to more, I guess, central type facilities. I don't know if you used any, Josh, or whether it was all just based on your...
So the Calford I performed was on a pretty powerful desktop.
Yeah.
We're not talking like supercomputer or anything, but we're talking a pretty powerful desktop PC. Yeah. But I can also say that one of the main advantages actually of machine learning is the speed of it and how little computational power you really need. Like, most of the machine learning calculations I do are just on a bog standard laptop, and they take anywhere from a couple seconds if it's the simplest to a couple minutes, and you can get through millions upon millions of predictions in that period of time.
But with that, is there not a thing about, because a machine learning algorithm has to be trained initially, right? You have to teach it essentially what it needs to do before it can do that. How long does that sort of time period take?
Well, depending on the models that you pick and the size of the data that you have, again, it's a pretty fast process. It's on the scale of minutes, whereas the most time-intensive part is actually the construction of the data itself.
Right. Before you start training, you have to construct the data that you want to use, and that can take hours upon hours to run the calculations. Again, on just like a laptop, nothing majorly powerful, but that's really the most time-intensive part, is the sort of pre-setup ready for your training. Once you've got your setup done and everything's ready, the training and the actual running and the making the predictions is pretty very quick, pretty rapid. Yeah. And what about you, Hector, with your models? Are they similarly on a desktop or a laptop, or do you use the high performance computing clusters and things?
Yes. In terms of then, just to give you an idea, yes, we go towards the high performance clusters. Just to give you an idea, if you look at the type of calculations, you're interested in working out whatever is the property or some deformation mode of a point within a material, and we're usually interested in solving this for millions upon millions of such points at the same time, and they're all interconnected. So we then have to use a bit of more computational power. So we use some of the high performance computing clusters you mentioned, which enables us to basically access lots of cores. And having lots of cores is
all the power at once.
That's right. Sometimes I feel like getting myself a cat and giving it the old stroke. You feel like the master of the universe. What can you do today? But the type of models we do are very computationally expensive. So, for example, what does that mean, computationally expensive? It generates lots of data. Okay, so you need to be able to store them somewhere. That's another problem also, not just running it, storing the large amounts of data that we generate for a given simulation. So that gives us a bit of a headache. taking it out, and then processing that data gives us a bit of a headache. So basically, a typical calculation that we will do may last a month.
Wow.
One run.
Okay.
So and within that run, we're looking what we say millions of degrees of freedom. We're trying to understand the advantage of the waiting for this long. Some people say, Hector, we want it overnight. I say, no, I can't do it. I can do it over several nights, over a period of a month. But the advantage of that is you get an enriched data set. So this is linking back to your machine learning question, the data sets that you're mentioning. So the simulations, hopefully we have models that are robust enough and trustworthy enough, the validation aspect. Not only will you get the property that you're seeking, but there'll be a set of other information. So for example, microstructure distributions, there will be information at the microscale, nanoscale about the stress states, which you will probably go to some large facility and fire some neutrons or X-rays to try and get that data. We'll basically, that data will come out from the model. And so what that will be equivalent to maybe to do this over a year or 1 year and a half, to do this experimentally to get the equivalent data set. But we could do it between a month and 2 months computationally. But in order to achieve that, we need a bit, lots of cores. And we do have also, because sometimes we're all competing, everybody wants to get access to the high performance clusters over here. So in terms of machines, we do buy some very kind of high spec desktops. And each of those desktops, we're talking over 30 cores, we're talking 40 cores and so on. We need more. And this is a problem now in terms of where do we go next. So what I mean by that is that how do we speed up calculations, Josh, and talk about machine learning. And it's true. Once you got a machine learning model, it's quick, the surrogate models, and you will use the surrogate models once you train them. But to get the data, one thing is do experimentally in conjunction with some of the kind of multi-scale models that we're talking about, and they're expensive to run. So one thing potentially in the future will be to move away from some of the kind of paradigms that we use now, like optimizing software, optimizing codes. Because I think over the last 30 years, I think everyone's done a pretty good job of optimizing codes. So I think the next challenge for us, and this will be to talk to our colleagues at computer science, will be to how do we start now coding these codes directly on the chips?
Right.
So for example, start using FPGAs, for example, to take advantage of these technologies, where now the calculations are done right at the cores. And now, you can imagine in the future, we have this rack that does specialist calculations for thermodynamics, right? And we maybe a rack that has specialist calculations for 3D printing of metallic systems. I could see that's where we should be going towards the future. But just to touch a little bit on this kind of model, if I can back to the machine learning, because I find it very fascinating. It's something that is getting close to my heart. And I'm trying to learn a little bit more. I find it a fascinating area because machine learning and AI is probably what the 1950s was when numerical analysis was coming out. All these numerical methods, everyone, you had Laplace and Behaviour, there was differential equations, and everyone trying to do everything analytically. And then computers came, and then this new world came of trying to things do numerically, try and run simulations, create what I call animations, but that with some scientific undertones or principles that you want to extract. People develop techniques how to approximate gradients, derivatives, integrals, and we're now in a similar era where we got AI and machine learning. We're trying to figure out how to use it. We know it deals data, and we're trying to learn how to use it. But one of the things I find that you mentioned, we need more data. Every time I talk to a machine learning person, they say, I need more data. And in particular, when you try and extrapolate, right? Yeah. We had so amazing success with AI and machine learning. It's incredible how powerful it is. But in terms of the material science community, you talk about image recognition. So, it's been fantastic. Medical applications have been fantastic. But one of the main things for me as a material scientist, and we touched about this, about new materials exploration.
Yes.
Being able to do this means extrapolation.
Yeah.
And an extrapolation to a space where as you mentioned, it takes a bit of time for you to prepare all the samples, prepare the right experiments. And with all the will in the world, that could put you off after a while, right? But, the point is, it's a challenge, right? And so I think there are two things that need to be addressing here in terms of physics-based models. Physics-based models supported by the right type of experiments can provide that extrapolation data. They can provide you an idea what the mechanisms that are operating outside those trained data sets and how those mechanisms that govern properties or microstructure are changing, because then you can connect that to composition, and you, through machine learning, once it learns that, you can now have a direct correlation between how materials behave, what are the principles driving that behavior, and linking it back to composition, and therefore enable us to do that exploration that you mentioned at the beginning. How do we go about deciding new alloys?
Yeah.
And I almost ran out of breath. I almost forgot to breathe there. So, but I think, and I think this is the thing with machine learning. You said everyone's using this everywhere, but I think one of the other challenges, what is this data kind of approach to it? Because material science is so data driven, we think data, and that's great. But you're always going to be limited, or not limited is the wrong word, but you always have this challenge or this wall about the data set that you're dealing with. So one of the things, and particularly with colleagues, with other colleagues in the UK, trying to work is how do we approach in a different way?
Yeah.
So the training, instead of data, how do we start developing AI, machine learning techniques, data-driven, whatever you want to call them, that actually start extracting physical principles?
Yes, yeah.
So you train them on
hybrid of the systems.
So an example is PIMS, right? So you got physical informed neural networks, right? And I don't see that reduced very much in material science context, but I think that will be a great approach where you start looking at what are the physical laws, you extract it out from measurements. And I think in material science, it's a great space, and I'm hoping talking to my computer science colleagues to come over, it's a great space, to try and develop these methods, right? And to try and to develop techniques where you extract principles as opposed to just correlating and connecting data.
And I think bringing us sort of almost full circle back to where we started, this is where, material science as an interdisciplinary subject really starts to come together, working, as you say, you almost a plea to the computer scientists, but to work closely with the people in the different disciplines to bring that understanding together, to combine these different models and different ways of approaching the same problem to come up with a sort of combined solution that can get us much further down the line.
Absolutely.
So
absolutely.
Yeah. I think that's a brilliant place to end. So just before we finish off, are there any final comments from anyone? Anything they'd like to add about modelling in general, material science, predicting materials? Hector, do you have any final thoughts that you wanted to add?
Yeah, I think material science, just science in general, but for me, for material science, I love this idea of interconnectiveness, right? It's an interdisciplinary subject. It's a beautiful subject. Materials where you see
very elegant. It's very beautifully elegant.
It's you see structures, different types of structures that evolve. You see patterns. When you compare this into a computer environment, you create art. Some of the images you can create, they look like abstract art. So I know it sounds a bit cheesy there, but I love the fact that we can try and understand a lot of physics through materials. I mean, one thing we didn't touch about materials is what is a material? Some of the material science that's pinging into biology.
Yes.
We have colleagues that are working with DNA, for example, and it's not just biomechanics. So this is the beautiful thing of materials, that this boundary is not there. It's just about how imaginative you can be. And with computational modeling and theory, you can start connecting some of these principles. And what I would like to see is more people joining us.
Yeah. Oh, it's that wonderful. It's such a rich space, both, as you say, in terms of materials, from, biomaterials to physical, but also in the other sort of axis of sort of thinking about from, modelling to very practical. And essentially there's so much to explore within that space. There's just so much to look at. It's a
lot of fun. It's a lot. All I would say, maybe I could have said all of that by saying it's a lot of fun.
It is a lot of fun. It is a lot of fun. Josh, have you got any final thoughts or comments?
Just agree with what Hector said. As someone who comes from a physics background, material science has really surprised me with how interdisciplinary it is. So I'm a physicist doing material science who also works with data science and does a lot of computer science, machine learning type stuff. It's just a really broad range.
Yeah. And I think it's one of the reasons that we all find material science so interesting and fascinating as a subject. So With that, we'll leave predicting materials properties behind for this week. We've covered a lot of things, from different types of modellings and computational power and why it might be useful for describing the materials properties in a whole different range of length scales. So for now, let me thank our two guest specialists this week. Thank you, Claire, and thank you, Hector, for joining us.
Thank you for having us.
And thank you, Josh, for joining us as well.
Thank you very much for having me.
And finally, to our listeners, thank you very much for tuning in. Please do join us next time, where our topic will be making the samples. Thanks very much for listening. If you want to join the conversation, you can find us on Instagram at Materials Unlocked. If you want to find out more about the topics that we've covered and the work that we do, a link can be found to our website in the show notes. Our thanks to the Advanced Metallic Systems CDT, the Henry Royce Institute, and the Department of Material Science at the University of Sheffield. See you next time.